Hello all, this is the video answer key to the review guide that combines units H's and I's solutions. The test is on April 10th, 2025, and it'll have a couple matchings, some multiple choice, and some free response. The point I want to make clear is you should understand how the labs for these units have worked. Questions about the lab could be a sample question for a free response idea. Okay, the first question can be skipped for 2025. It uses something called the ideal gas law. The formula for the ideal gas law is pressure times volume is equal to the number of moles times some constant value times the gas law. It's called the gas law constant, and the temperature. So this is where all of the individual gas law relationships come from. And so the larger equation for the ideal gas law includes all four variables and a constant. We have not done any practice problems with this formula, so there won't be any questions that use this. Question 2 shows you three different variables. It tells you a volume and a temperature and a pressure. But then it only changes, it asks for the new volume because the volume is changing. And the temperature at the beginning and the temperature at the end are the same. So the pressure is really the only thing changing. So if you're changing the pressure and you're measuring the volume, that's Boyle's law. Boyle's law looks like this. P1 times V1 equals P2 times V2. So the values that are given in the problem tell you that the first volume is this and the first pressure is this, and asks for the second volume at the final pressure. The final pressure is the standard pressure. And for millimeters of mercury, the value for standard pressure is 760 millimeters of mercury. When you rearrange the equation to solve for V2, you just take pressure 1 times volume 1 divided by the pressure at the end. If you plug these numbers in to this equation on your calculator, you get a volume at the end of 2.5 milliliters. The last step that I ask students to do is ask themselves, is this number reasonable? So if the pressure goes from 34 to 760, that means this number goes way up. So, it goes from 55 to 760. If the pressure goes way up, look what happens to the volume. It goes from 30 all the way down to 2. Okay, so this number goes up by 15 times. If you take 760 divided by 55, it's about 15 times. If you take 34 and divide it by 2.5, that's also about 15 times. So this number does make sense because if the pressure goes up, the volume's got to go down. The second question actually also deals with Boyle's law. So you need to use pressure and volume again to determine the final volume. So here are the givens. Rearrange them into this equation. If you allow V2 to be all by itself by moving P2 to the other side, then the volume at the end is 99.0 milliliters. So we should answer this question the same way as we did before. We should ask if it's reasonable. So the pressure goes down, which would mean the volume should go up. So it does go from 98.5 up to 99. And it's true that this is a small change in pressure. This is a relatively small change in volume. The next page has some definitions and some recall items, so you can solve those questions on your own. I did want to demonstrate how to do some of the conversions. It is important that you understand how to convert between Kelvin and Celsius, and these are the two ways. This number is measured to the 10th place, so then you should use this value for converting. This one only goes to the ones place, so you only need to use 273 as your conversion. And this one goes from Celsius to Kelvin, so you have to add 273 to the Celsius temperature. This one goes from Kelvin to Celsius, so you have to subtract 273 from the given value, so 376. So here are the answers for the temperature conversions. The next three questions are pressure conversions. They're literally just dimensional analysis, so you need to understand this relationship, so that if you have 790 millimeters of mercury, you just divide by 760 to get 1.04 ATMs. You probably could just round this to 1.0 because there are only two significant figures here. I just wanted to show that this is the process. Okay, the next question asks you to go from kilopascals to torr, and so here's an equality from kilopascals to torr. So you set up the dimensional analysis so that the kilopascals will cancel. You should be left with 1,005 torr. This measured value at the beginning has 4 sig figs, so your answer should have 4 sig figs. The last question asks you to go from ATMs to KPAs. So here's an equality that relates ATMs and KPAs. So 1.76 ATMs times 101.3 divided by 1 gives you a final answer to 3 significant figures of 178 kilopascals. The next questions are now from the solutions unit. So the first and second questions both use the formula to calculate molarity. And molarity is the concentration of something as a ratio of moles of solute to volume of solution. Okay, so the first question is, what is the molarity? That means concentration is the unknown. So you should write literally C equals and then leave a blank. Or maybe a question mark if you want to show, like, I need to solve for the concept of concentration measured in molarity. Well, it gives us grams of calcium chloride. So that's actually M. I know the equation is C equals N over V, but grams measure mass. So we've got to get to N, which means we're going to change grams into moles. So to go from grams to moles, you need the molar mass from the periodic table. And when you do this calculation, you end up with a number from the calculator that has more places than this, but it's 0.0437, etc. One important idea for volume, if you're going to use molarity, molarity is moles per liter. If the measurement is in milliliters, they have to be converted into liters. So the step is to show that there are 1,000 milliliters in 1 liter, which means you just have to divide this by 1,000. So 206 divided by 1,000 is 0.206. So that's this conversion right here that's being demonstrated. So here is the number of moles for calcium chloride. Here is the volume for the solution. And so when you take the moles divided by the liters of solution, you end up with 0.212 molar. That's the way you would say the concentration. Question 2 asks you to do this same calculation, except that in this example, gives you a different chemical, sucrose. It also gives you the mass, though. Mass is measured in grams. For the concentration equation, you need to get grams into moles. So the first step I did was changed grams of sucrose into moles of sucrose. Looking at the molar mass, you just have to add up 12 carbons, 22 hydrogens, and 11 oxygens. So each of those compounds is a pretty big one. Man, I'm really sorry. Excuse me. So when you take grams divided by the molar mass, you end up with number of moles. Once you have the number of moles, then you can use it in the concentration equation. Concentration is moles divided by volume, which gives you a final number of 0.415. And because the value from the problem only had 2 significant figures, we should round the second significant figure to be 0.42 molar. The third question asks you a different way of solving it. It asks you how many grams. So now we have to solve for N. It gives you the concentration because molarity measures concentration. Because it gives you concentration and asks for N and gives you volume, you can rearrange this equation of C equals N over V to be N equals C times V. After you substitute the values in for C and V, you get a final number for number of moles to be 0.80. The question asks, how many grams do you need, though? So we got to get to M. We have N now, so this is number of moles. So you got to go from moles to grams. To go from moles to grams, you need the number from the periodic table. And if you set it up so that moles cancel, you need grams on the top. So 0.8 times 58.44 gives this number from the calculator. But from the measured values given in the problem, 3.2 and both 250. They both only have two significant figures. So your answer should be rounded to two significant figures. So that's 47 grams. The last question deals with a dilution problem where it tells you that you need a sample of 355 milliliters of 6.22 molar hydrochloric acid. That's what you need to end with. So this is kind of a tricky way of saying it, so that this is the concentration at the end and this is the volume at the end. Because the stock solution is always solution number one. The first concentration is the stock solution. So the stock solutions come in these like giant jugs. And you have to move a solution from here to here. Even though there's like 2 liters probably in this entire container, the first concentration is 18.99, and the first volume is the amount that is moved. It's not the amount in here. It's how much gets moved from the first scenario to the second scenario. And so that's the volume that you need to solve for. When the question says how much stock solution will be used, that's the volume. So the equation to calculate a dilution is the concentration of the first one times the volume of the first one. That will be equal to the concentration of the second one times the volume of the second one. And the final volume is really volume of one plus the volume of the water. Because when you dilute it, you just add water to it. Okay, so you can solve for V1 by taking the concentration of the second one times the volume of the second one and dividing by the concentration of the first one. So the volume that needs to be moved from this jug into the final container is 0.116 liters, which that's 116 milliliters. Now, since the final volume is supposed to be 0.355, how much water is needed is just the final volume minus the amount that's moved. So the total volume at the end needs to be 355 milliliters. If 116 milliliters are coming from the liquid, you need 239 more milliliters to make a final volume of 355 milliliters. So this is the solutions for amount of original solution moved and final amount of water. The next questions are all vocab questions. I'll let you look up these terms on your own. You should use the textbook or the internet, a reliable source, of course, to give a reasonable definition for each of these as it relates to class. We haven't used the words miscible and immiscible, but I think they're helpful, especially when we're talking about liquids mixing together. And so those are things you could look up on your own. That's all I have for this review guide. If you have any questions, feel free to see me before the test. Otherwise, good luck. I hope you do really well.